Okay. Can we fix this? Okay, so now that we've finished RSA's concepts, we want to ask naturally, what is RSA, or should I say, how is RSA used in the real world? So in RSA, there are state-of-the-art libraries which are extremely fast, and they are normally written in C instead of Python, because C is faster, and they are usually used to implement RSA. However, humans make mistakes, and there can be vulnerabilities, or should I say, there can and will be vulnerabilities. So, moving on to the security of RSA, we need to factor n to get phi of n, which is hard. And we cannot decrypt without knowing P and Q, because we don't have phi of n. And NIST, or the US National Institute of Standards and Technology, recommends 1536-bit P and Q, or 3072-bit n. And this is for 128-bit security, which is considered the gold standard. So what 128-bit security means is that you will need to brute force 2 to the power of 128 in order to get the factorization of n. And in cryptography, 128 bits is normally the security that is the go-to level, as it takes like millennia to brute force. However, in CTFs, 1024-bit n is secure enough because it takes like a few years maybe. But the reason why we use smaller primes compared to the state-of-the-art implementations is because to generate primes, it takes some time. And so, for convenience sake, we want 512-bit primes in order to generate the primes faster. Not to say that it's slow to generate 1536-bit primes, but it takes like a few seconds, which is kind of slow for our standards. But again, humans can and will make mistakes. So many vulnerabilities will lead to attacks on RSA, and this is not unique to RSA. Many other crypto systems also have attacks. And in this case, RSA has many prevalent attacks, and they are very well known. We will be going through 4 of them today. So some multiple of P is given, 2 ciphertexts with the same n and co-prime E, hashtags broadcast attack, and the Franklin Ritter related message attack. But the list goes on. So first, let's start with some multiple of P being given. So we recall our RSA setup, n is equals to P times Q. So n is equals to P times Q. And suppose we are given some K times P. So let's just say H for heat. K times P. H equals K times P. And K is large and unknown, so we cannot factor K times P normally. But can we recover P? The answer is of course yes. Next slide. So we can use GCD. So we notice that n is equals to P times Q, and H is equals to K times P. And Q is a prime. So as long as K is not a multiple of Q, we can get P is equals to GCD of N and H. Everyone following so far? Okay. So with that, once we have P, we can decrypt the message. And finding P with GCD is fast, unlike factoring. If you're wondering, the time complexity of GCD is O log of N, where N is the larger number. So now we have another challenge called 3 primes. We'll be giving you about 10 minutes to do this. And as always, if you need any assistance or help, feel free to raise your hand. Let's take a look at the challenge. So I'm just going to close everything. So over here we see our challenge. We have a flag that is 47 characters is asserted here. So what the assert statement does is it throws an error if this false. So afterwards we have RSA, but we realize that instead of generating P and Q, we have P, Q and R. which is weird. But we realize that the reason the challenge does this is because we have n1 equals p times q and n2 is equals to q times r. Afterwards, the flag is split into two and is encrypted with the two ends. And we are given all of the outputs, namely the two ciphertexts as well as the two public keys, which are the n1 and n2. And we have e equals 65537. So let's take our outputs. And let's write our solve. So we recall that n1 is equals to p times q and n2 is equals to q times r. And if we go back to our slides, we see that we have some k times p. If we have some k times p rather, we can recover p because we have p times q. Over here, we have p times q and we have q times r. Evidently, the GCD of n1 and n2 is q. So what we can do is we can recover q. So we import GCD from math and we do q is equals to GCD n1 n2. Afterwards, since we have q, we can get p and r. So p is equals to n1 slash q, right? Let's run this. We have our print. Wait, that's weird. Why do we get some weird float in scientific notation? That's because Python does not check whether the quotient is a perfect integer. And so it will just result to float data type. And float data type rounds. So our large numbers will lose position and we will not even get our correct prime. So instead, let's do floor division, which will return the correct value because we know that n1 slash q, or rather n1 divided by q, is an integer. And we can do the same for r. And now we can decrypt both ciphertexts. So again, phi is equals to phi 1 is equals to p minus 1 times q minus 1. Phi 2 is equals to q minus 1 times r minus 1. And d1 is equals to pow 65537 negative 1 phi 1. And same for phi 2. So let's just do it. And after that, our m1 is equals to c1 to the power of d1 modulo n1. And same with m2. And after that, we can import long to bytes from PyCryptodo, and we can convert both those messages back into bytes. So flag is equals to long to bytes m1 plus long to bytes m2, and we can print the flag. And if all goes well, we should be able to get our flag. Oh, I did seem to make an error here. R is n2 slash q, or n2 divided by q. Yep, we got a flag. I.YCEP more primes does not mean more secure, which is the case here. So I'll go back to the code for you all to copy. I'll give you about 1 minute to copy. So we'll be back at 49. We'll be moving on to our next attack. Okay, so now that we have completed RSA with some multiple of p being given, we are going to move on to RSA where we have two ciphertexts with the same n and a coprime e. So let's say we are given two ciphertexts that are encrypted with the same modulus n, but our public exponent e1 and is different, or rather, our public exponent e is different for the two different values. So let's say C1 uses E1 to encrypt and C2 uses E2. And we have E1 being coprime to E2. We can recover M with this information. So first, we want to go back to Bizarre's identity and extended GCD. So if we recap to the identity, we can see that given two integers a and b, there exists integers x and y such that ax plus by is equals to GCD at a and b, as well as the fact that xGCD finds said integers. So this is just restating the identity. So if we go back to our scenario, we can see that E1 and E2 are co-prime, which means that GCD of E1 and E2 is equals to 1. Next slide. So this means that using Blizzard's identity, we can find A and B such that A times E1 plus B times E2 is equals to GCD of E1 and E2, which is equals to 1. Everyone following so far? Okay, nice. With knowledge of this, next slide, we can find A and B using xGCD, and after that, we can raise C1 to the power of A and multiply it by C2 to the power of B. And let's simplify this by substituting in C1 equals to m to the power of E1 and C2 equals m to the power of E2. So let's do m to the power of E1 to the power of A, and you go to the next line, times m to the power of E2 to the power of B, which from here I'm going to go back to the other whiteboard because it's not enough space. So if we continue on from here, we have is equals to m to the power of A times E1 times m to the power of B times E2. Everyone following so far? You all know how I got from here to there? Alright, great. So from here, we can simplify again by doing m to the power of A times E1 plus B times E2. So quick question, how did I get from how did I get from here to here? Anyone want to answer? How did I get from this line to this line? Yeah, log indices. So specifically, x to the power of y times x to the power of z is equals to x to the power of y plus z. So this is what I'm using. So after this, we realize that if we go back to our identity, or Blizzard identity, this A times E1 plus B times E2 is 1, which means that this is equals to m to the power of 1, and we have gotten our message. But one thing that I didn't mention is that if we want to do m to the power of some negative number, we will arrive at a fraction which is not supported in Python. So instead of that, we want to work modulo n, so that we will get an integer when we do negative exponentiation. So let's just change everything to congruent, and because all the index laws, multiplication and addition all hold modulo n, we'll be fine. So now, moving on, we have another practice challenge called 2 ciphertexts, where we'll give you about 15 minutes to do the challenge. And as always, if you need any help, feel free to raise your hand. Okay, so we're going to go take a look at the challenge. It's 2 ciphertexts, right?
Yeah, 2 ciphertexts.
Alright. So again, we have our standard RSA setup. And as per our scenario that we went through earlier in the slides, we have 2 primes, E1 and E2. Wait, they're not primes, but we have 2 exponents, E1 and E2, that are used to encrypt our flag. And again, we have the 2 ciphertexts, hence the challenge name, as well as the modulus. So let's just transfer our values over to our solve script first. And let's first find the GCD of our 2
exponents. So the two exponents are 314159 and 2653589, which are, if you're wondering, the first 15 digits of pi. I did not print it. Yeah, it's 1. So they are co-prime, which means that we can use our attack. So if we go back to our slides, we can see that we want to use XGCD to find A and B. So what we can do is we can go to our Discord and we can get our utils.py. We can get our XGCD function from utils.py, which give me a second to grab it. Here. And so we can get our GCD, but first let me define E1 and E2 for easier use later. So we can get a GCD of E1 and E2, and we can see that we have negative 79,390 times E1 plus 9,399 times E2 is equals to 1. So what we can do is we can get our message by doing C1 to the power of C1 to the power of, I did not define the variable, C1 to the power of A modulo n times C2 to the power of B modulo n. And we can take the whole thing modulo n. And by right, this message should be the correct message that we originally encrypted. So what we can do is we can get our long to bytes again and convert it back. Yeah, we get our flag, which is 3 primes, 2 ciphertexts, and 1 crypto system. So I'll go back to the source script and give you all about 2 minutes to copy. So we'll be back at 2:20.
Okay, so now that we have completed these two attacks, we'll be moving on to our third attack, called Hashtag's broadcast attack. So let's say that we can encrypt a message multiple times with the same E but with different N. We can recover N. Next slide. So let's have a brief segue into a theorem called the Chinese remainder theorem. Okay, so let A and Ni, so like N1, N2, N3, be integers. And let's say that we know A is congruent to 5 modulo N1. A is congruent to 6 modulo N2. The Chinese remainder theorem states that we can recover A modulo the LCM of M1 and M2. Exactly. So we can also generalize this to more than 2 moduli. So let's say we know A is congruent to 7 modulo N3. We can recover A modulo N1, N2, and N3. Everyone following so far? Make sense? Why we can recover N1? That we can recover A modulo N1, N2, N3, or rather their LCM. Okay, if so, moving on. To implement CRT, we can use the CRT function from SimPy. So David will be demonstrating now.
So if you were to go to like any like regular Python REPL shell, we will be, so you may have to pip install this. So from simply.n3.modular, import this function called CRT. CRT is the Chinese remainder theorem. So let's say I want to find x, where I know x is 1 mod 5, followed by 2 mod 6, and then 3 mod 7 for example. So if I were to put my remainders as 1, 2, 3, and then my moduli, which is plural for modulus, as 5, 6, 7, when I run CRT moduli remainders, I get two values over here. I'll give you guys a while for you all to type this in to also experiment it. So there are two values given by CRT. One is 206 and one is 210. If we were to look at these two, right, the left one, or the first value, is going to be our x, and the second value is going to be the LCM of 5, 6, and 7. So how do I know this? Because 5 times 6 times 7 is 210. And so what CRT does is that it returns x followed by the LCM that is modulus 2. So typically, if I want to just find x directly, I'll index it with 0, and then this will give me the value of x. That is more or less it. If anyone needs help with pip installing SIMP for CRT, do raise your hand later and we'll come over to assist you. Yeah.
Yeah, and so over here we have 206 is congruent to 1 modulo 5, is congruent to 2 modulo 6. Yeah, I'm not going to write out the third one, but it is congruent to 3 modulo 7. So now we'll move back onto the slides.
Can you give them a challenge maybe?
Sorry? Okay, so we have A is congruent to 7 modulo 20, A is congruent to 5 modulo 31, and A is congruent to 6 modulo 42. So I'd like everyone here to try out using CRT on your Python. So try and CRT these three together. Okay, sorry, 6 modulo 43, the other one has no solution.
So in our example here, we're trying to find y with mod 20 is 7, mod 31 is 5, mod 43 is 6. We just do CRT 20, 31, 43, followed by the remainder 7, 5, and 6. And you see that we get 26107, modulo 26660. So answer is 26107. That said, let me ask a question. If I were to replace 43 and 31 here, right, and then I replace 6 and 5 here, would this also output the same value? Yeah. If I swap 43 and 31 and 6 and 5, will this output the same value? Yeah, correct. CRT, as long as your ordering is correct, it will always output the same value. Yeah. That said, remember that it's the modulus first, followed by the remainder.
Yeah.
And then we'll move on with the workshop. If wait, anyone has any questions regarding this?
Why is my number different?
Wait, what do you put in for yours? What's your inputs?
20, 31, 43, and 765. But I got.
Oh, it's 756. The remainder is 756. Mod 31 is 5. Yeah. So you have to be very careful of like the ordering of your modulus and remainders. Yeah. Okay.
Okay, moving on. Back to Hastad's broadcast attack. So we notice that we have multiple different ciphertext modulo different moduli, but the left hand side, which is m to the power of e, is the same because we have m that stays constant and e also stays constant. So doesn't this look a bit familiar? Well, the answer is of course yes, it does. Next slide. So consider this. What happens if m to the power of e is less than m in I.YCEP? Because we take the lowest positive value of m to the power of e that is congruent to, we just get m to the power of e back. And we can just take the e through of n. So, no, sorry, e through of m to the power of e, my bad. So, I.YCEP uses e equals to 65,537 to prevent this, because 2 to the power of 65,537 is much larger than n for normal I.YCEP, which is about 3,000 plus bits. And the reason why we are using 2 to the power of 65,537 is because 2 is the smallest possible value that you can encrypt, because 1 will just give you 1. But we can apply this for our attack. So let's say we have at least e ciphertext. And if we have at least E ciphertexts, the lowest common multiple of those E moduli will be more than n to the power of E, because m is less than n. So we can get n to the power of E in full, and we can get m by taking the Eve root. So that is in essence how Hassel's broadcast attack works. Next slide. So here is a demonstration on how we can do the nth root in Python. So we'll be demonstrating now.
Alright, so you have to pip install a different library now. So while we have transcendental theorem, we are going to need to install a new library called GIMP2. Hold on. So from GIMP2 import iRoot. If you don't have GMPY2 installed, you will have to pip install it again. But what iRoot does is that it's a very handy thing that lets us do square root, cube roots, nth roots. So what do I mean by this? So for example, let's say I have 49 and I want to square root it. If I call iRoot 49 2, it's just going to do the square root of 49, which will give us two values, 7 and true. 7 is going to be the square root, rounded to the nearest integer. True and false will determine whether or not it's an actual square root or not. So like for example, if I do 51 for example, 51 is not a square number, right? This will give me 7 and false. Because when you square root 51, the integer part will be 7 point something 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 something, and it will return only the integer part, which is 7. It returns false because 51 is not a square number. So as an example, right, let's say I want to input 178 to the power of 129, and then I root it by 129. You'll see that it will return 178 and true because it is in fact 178 to the power 129. But if I let's say add a +1, it will return 178. It will still return 178 because that is the integer portion, but it returns false because it is not a proper it's not 178 to the power 129 essentially. So quick question, if I put in -1 here, what would the left hand side be? Will it be 178? I heard a no. Why? What do you think it will be? Correct, it will be 177. It always rounds down for iRoot. So we can keep that in mind. And one last thing is that if you're trying to, let's say, find the 129th root of a value, for example, in order to isolate the value, we index with 0 to get mpzec 178. The issue is that iRoot returns something in a mpzec data type. So we want to convert it back to an integer. So if you want to do iRoot of something, we have to do int iRoot object 0 index. So for example, in our case, if let's say E is more like 3, and our value is let's say the message this, and it's to the power 3, we will just do int iRoot our cube root, cube root it by 3, and we take the 0 index and we convert it back to an integer. So as one last example, if I were to do 729, which is 9 cube, to do int iRoot, we just iRoot it and then 0 with 3 as the nth root that we're going with. iRoot is very useful because it basically lets us do cube roots, square roots without much of a hassle. So for example, if by any chance you have if you want to use the quadratic formula with a square root of the determinant, you can use this to complete the square root essentially. Yeah.
Okay, so again, wait, can you go? Again, second one. iRoot returns the data type mpz for efficiency reasons. So we need to convert it back to an int. And one more thing, we cannot just take, let's say we want to root x, we cannot take x to the power of 1 over n. Maybe 1 cube root, we cannot do x to the power of 1 over 3 because that returns a float. And floats again have rounding, so we cannot do that for large numbers.
So I think it's best to give a demo. So for example, how Python stores data types like float is that if I do 0.1 plus 0.2, it's well known that it won't be accurate. There's always a 0.4 at the end. There's some reason behind it, but we will not cover that because it is usually not. It's more so related to how the floats are represented in bits. That's it. If we were to do something let's say 27 to the power 1 over 3, you'll see that in this instance, oh sorry, I need to do this. It still gets 3.0, but the thing is when we go very big numbers, it will always return with some decimal points, and with that it's not very, let's say trustworthy-ish, I suppose that would be the term. So let's say I do 178 to the power of 129, and then I try to do the power of 1 over 129. Okay, in this case it seems it works lah, but I think when the number gets very big, it will have some rounding errors. So for now, I would recommend just using iRoot instead, where it's a lot more like safe.
If your number is more than 53 bits, it will cut off the last part.
Yes, that too.
Okay, next slide. So now we have another challenge called 3 ciphertexts. I'm so original, guys. We'll give you about 15 minutes to do this challenge. And again, this challenge references Hasnat's broadcast attack. So we'll go back to the slides.
I saw that quite a few of y'all managed to solve it, so good job. We'll be going through it now. So let's take a look at the challenge first. We can see that this is exactly the same scenario as in the slides. So we have our E value, which is 3, and we have our flag, which is converted to an integer, and that is being encrypted, so it's M. Afterwards, we have 3 times of encryption. So for each time, a different P and Q are generated. And afterwards, we make sure that M to the power of E is more than N, so that we don't end up having someone cube root our ciphertext. And afterwards, we encrypt each message and we append it onto a list. And we also append the public modulus to a list. Afterwards, we have the ciphertext as well as the modulus. So now, let's grab our values and let's create a soft script. So we know that we're going to be using CRT in this challenge because it's a Hasnat's broadcast attack challenge. So let's import it. And after that, in a second, I need to check something. Okay, so after that, we can go back to our slides and let's check our attack again. We can see that what we need to do is we first need to recover M to the power of E in full. So we can do this by doing CRT, N, which are the moduli, and C, which are the ciphertexts. So if we run the soft script, we'll get our M to the power of E in full, and we'll get the modulus, which is irrelevant because we are looking at M to the power of E here. So we can just get our M to the power of E by doing a CRT, and let's take the first value, which is the result. Afterwards, let's call the variable M power E, and we can define it. And afterwards, we can import iRoot from GMPY2, and we can get M is equals to int iRoot of M power E, E which is 3, and we index out the true value at the second return value of iRoot. Everyone following so far? I just said a lot of words. Alright, great. So now our M should hopefully be the flag. So as David mentioned earlier, we can check if we got the correct M by checking if it's small. And our M is this small. And let's take a look at our N. It's much longer. It's like 2 times as long in terms of digits. So it's probably correct. So let's get our long 2 bytes from our PyCryptoDome. And we can convert our flag to bytes. And yes, we have gotten a flag. At this rate, all of today's challenge names are going to start with a number. After writing this, I made sure the last one did not start with a number. But yeah, we have successfully performed Hastart's broadcast attack. I'll give you guys maybe like 1 minute to copy the code, and after that we'll move on to our last attack of RSA for the day, which is Franklin Rater.
Okay, so now we're moving on to our last attack of the day, which is the Franklin Rater. Okay, correction. Last RSA attack of the day, which is Franklin Rater related message attack. Next slide. So, before that, we are going to introduce you to SageMath. So SageMath is a interpreter built atop Python, which means that you can run Python code really easily, and it works out of the box. And other than that, it consists of many functions that are very useful for cryptography and math in general. So we will be going through some of these examples later. And you can code in Sage in .py files or Python files, or .sage files, which are Sage files. And we can run the files with Sage, file.py or file.sage. So SageMath has a lot of algorithms that are implemented. For example, GCD, XGCD, and even CRT. But take note for CRT, the inputs are swapped as compared to SymPy. So in SymPy, your inputs are, for example, your moduli first, and afterwards your results. But for SageMath, your results come first, and then your moduli. So keep that in mind. And these functions can of course be called with their arguments just like in Python.
So for example, if you guys have Sage installed, you can just do like Sage here, and then it will open this Sage terminal. If you don't have Sage, it's also fine. We can direct you to Sage Cells server, which is a website that lets you run Sage code. We'll write this down on the whiteboard later. But in Sage, for example, a lot of functions are already inbuilt. So for instance, if we do like we can have GCD. We also have XGCD, which works the exact same way as the code before. So for example, here we can check that -1 times 16 plus 3 times 6 equals to 2, which is the GCD that is given. You also have CRT. But for CRT, do note that instead of moduli first then remainders, in Sage it is remainder first then moduli. For example, in here, right, I'm trying to find a number that's 2 mod 5 and 3 mod 7. The remainders go first in Sage. Whereas in Python, the CRT module from SymPy, you reverse the order. Yeah, there are also many other functions that are quite helpful, but we will go through them as we encounter them.
Yeah, and also one more important thing, other than the one on the slide, is that SageMath code is basically Python syntax. So you can run a print hello world and it will work. And you can copy your Python code into Sage, and there's a 90% chance it will work. And the last thing on the slide about algorithms in general is that it's impossible to list all of them. So we recommend using the SageMath documentation, and it is very useful from our experience also. So SageMath also has custom data types. For example, this thing, which is basically an integer modulo submodulus. And these can be used to define polynomials or integers modulo n, like the earlier data type. And again, this is extremely useful. So now moving back to RSA, or the Franklin Rater message attack. Let's say we encrypt two messages M1 and M2, where M2 is equals to M1 plus K. So it could be M2 is equals to M1 plus 3, where we know 3, because it's right here. We can recover both messages. So let's take a look at how the RSA encrypts its messages and the equation. So C is congruent to n to the power of e modulo n. In fact, does this look familiar? It's a polynomial of degree e. And recall that in RSA, our e is usually small and known. So like, for example, 65,537. So you can have a polynomial of manageable degree. And on the other hand, when we go back to our scenario where we have m plus k, where we know k, we have two polynomials, which are c1 is congruent to m to the power of e modulo n, and c2 is congruent to m plus k to the power of e modulo n. Everyone following so far? Alright, nice. These two polynomials share a common root modulo m at modulo n, which is m. So if we were to evaluate our polynomial, so c1 minus m to the power of e, it will be congruent to 0, and c2 minus m plus k to the power of e is also congruent to 0. So can we retrieve it? Yes, we can. Let me introduce you to something called polynomial GCD. So just like how integers can be factored, polynomials can also be factored. So this is the factorization of a degree 3 polynomial. Next slide. Since polynomials can also be factored, their GCD also exists. So for example, the GCD of these two polynomials, so x1 times x2 and x2 times x3 is equals to x plus 2. So, quick exercise. What is the GCD of these two polynomials?
X plus 7.
Yes, x plus 7, because you can see here they share a common factor of x plus 7. Next slide. So, polynomial factoring also works modulo p. So, let p equals 5, so we'll use p equals 5 here. And we have a polynomial x plus 2 times x plus 3. So, I'll be working that out here. X plus 2 times x plus 3 is equals to, we're going to expand this, so x squared plus 2x plus 3x plus 6. And we can simplify to x squared plus 5x plus 6. Yep. This is secondary 3 math, or secondary 2 math, I don't remember. And after that, we can reduce it modulo 5. So when we have a polynomial modulo 5, we reduce all of its coefficients modulo 5. So this means that it's 1 modulo 5 is 1. 5 modulo 5 is 0, so we omit the x. And 6 modulo 5 is 1. So this whole thing is congruent to x squared plus 1 modulo 5. Everyone following so far? Next slide. This is the same thing, but we are doing it for different polynomials. And next slide. Factoring polynomials modulo p is fast. So we can go from this to this quickly. But we can also perform a GCD modulo p. So I've already done the exercise just now, so we'll just skip this. The answer is x plus 3. Next slide. So now David will be walking through polynomial GCD modulo p in Sage Math.
So if you're Sage, otherwise like you can go to this website. You want to write it on the whiteboard, like sagecellserver.com.
6 is.
Yeah. So
There.
if you don't have Sage Math, you can go to this website called Sage Cell Server. It is a website that lets you run Sage code. If not, if you've installed it, as I believe we've put in the instruction guides in the welcome ceremony or at the start, you can also just activate Sage. So in this case, I'm already in my Sage terminal. So let's say we have p equals to 5, and then so we're gonna initialize a zn to be z mod p. What this means is that any number in zn is going to be modulo 5, p which is 5. So for example, zn 11 is going to give 1 because 11 is 1 mod 5. And at the same time, like zn of like let's say 1 to 9 is going to be 4 because 1 to 9 is 4 modulo 5. Now that we have a wait, so far everyone can follow this, right? I'll give you guys maybe 1 to 2 minutes for you all to open your Sage terminals or to go to Sage Cell Server. Alright, so now that we have initialized a z mod, we are then going to initialize polynomials. So to initialize a polynomial in Sage Math, you can do something like this, where we do r dot left arrow x, right arrow, equals the polynomial ring Zn. What this means is that we define a series of polynomials all in Zn, and then and the dot x here means that x will be our variable. What this means is that when we do x plus 6, for example, it will give x plus 1, because Sage will see x plus 6, know that the x belongs to the polynomial ring of Z mod 5, so any coefficient will be modulo with 5. So in here, x plus 6 is equivalent to x plus 1. And let's say like if I do 5 times x plus 1, it will just give 1, because 5 modulo 5 is 0. So far so good? Alright, so we're going to take two polynomials and we're going to perform GCD. So we have x squared plus 2x plus 2 and x squared plus 1. So we have f1 equals to x squared plus 2 times x plus 2. Note that 2x like this will not work. We have to use 2 times x. And then our other polynomial will be x to the power squared plus 1, I believe. Let me check. Yes, okay. So if we were to look at the two polynomials, over the regular integers, they don't have a common root. Because x squared plus 2x plus 2 and x squared plus 1, they don't really share the same root. But when working in modulo 5, these two do share a common root, which if we go to GCD of f1 and f2, we get x plus 3. So in this case, x plus 3 is a common root between f1 and f2. I'll keep this up for around like 2 to 3 minutes for you to copy. Is there any questions regarding this so far?
Yeah, I got syntax error. I can't find it.
Oh, what's the name of the syntax error?
How do I do? Because you're not in Sage. You need to open it. It's not in Sage. This is the Sage environment. You need to type Sage to open the Sage. Oh, okay. This is not
Oh, wait, I see.
That's what output. Because you didn't define your polynomial ring, so Sage thinks you are in integers. You need to define your polynomial ring. So over here.
Sorry. Okay, so now we'll be moving on to back to Franklin Rater. So recall that in RSA we work modulo n, but clearly polynomial GCD does not work modulo n, right? So there are special cases that polynomial GCD cannot produce a valid output, and Sage Math just outright says, no, you can't compute it. We won't be getting into why this is the case, but the probability gets smaller as the prime factors get larger. And in RSA, n has extremely big prime factors, so the probability is basically 0. So instead of calling GCD in Sage Math directly, we have to implement it ourselves. So we can just use the Euclidean algorithm with one small change. I'll be demoing it now. So let's generate our RSA modulus, which has really large prime factors. So p equals to get prime 512, q equals to get prime 512, and n equals p times q. We can then define the polynomial ring, which is Rx equals polynomial ring Z mod n. So instead of doing Zn, I'll just do Z mod n directly. And if we do x plus n plus 1, we'll get x plus 1 because our n plus 1 becomes modulo n, which is 1. Everyone following so far? Okay, I'll give you a bit to start your Sage.
Yes.
Oh, is it from crypto.util.number? Oh, okay. Just use. Yep, it's literally a Python, so you can just do that and then we'll shoot it's not Python.
Yeah.
You have Sage inside? Shoot, I just don't know. Okay, you type Sage. And then, looks like you won't Sage dot. issues with the notes. Oh, because you take the story from me, you take like you have to reset the control side and then and then rerun it, and then it should be the import should work. You have to install Sage, which do you install using Honda? I tried to do it install, then it's going to be
Oh, you need to install. Do you install
Sage
Microsoft?
is a completely different programming.
Okay, wait, can you
It's like installing a new language.
Just exit your Sage. You can just tap exit.
Okay, then if you have control inside, then you do Honda, activate, Sage. You will have to do this every time you like run, every time you open the
And you
rest
can
of
exit your
the
Sage and reopen
This
the
will
one.
see your base becomes Sage, that means Sage installed. Now we do Sage.
You tap Sage dash
You will
dash.
show the Sage every now.
No, Sage space
You
dash
can
dash.
shut up. Yeah.
No, dash dash. It. No, without the space. Dash dash space. Space. Install. Pycrypto. And click enter. You don't have Pycrypto. You kind of need to like run in your Python.
So after this, we are going to define our polynomial. So let's just get our polynomial 0 is equals to this. So like x plus 2 million times x plus 3 million. And we can define another polynomial to be x plus 2 million times x plus 4 million. So quick question, what would the GCD be? X plus 2 million, yes. But if we call GCD as we expected, it will crash. So we have to implement our own GCD. So let's do define poly GCD, and let's do if b is 0, we return a, and if not, we return poly GCD b a mod b. So that is the Euclidean algorithm, which we can just directly copy to get poly GCD. It works both on polynomials as well as integers. So after that, we can get our GCD. But oh wait, why is our number so large? Or why are our numbers so large? That's because when we go back to our poly GCD function, when we return a, we don't care about the coefficients. So in essence, we need to force this first coefficient to be a 1. So how we can do that in Sage Math is we can do dot monic, which will force our first coefficient to be a 1. So if we run it again, we get x plus 2 million. So to further illustrate what monic does, we can do 2 times x plus 2 million dot monic. It will give us x plus 1 million.
No, you need to press up to go back to the difference.
So everyone's following so far?
What are the poly 1 and poly 2 values? So you can make anything, you can do x plus 2, x plus 3, and x plus 2, x plus 4. It should be fine. Then otherwise, return.
Okay, I'll go.
Go back to the
Since everyone is a bit lost, if okay, can everyone who has like any issues raise your hand, then we can address them one by one.
So if you
Okay, so now we'll be going back to our attack. These two polynomials share a common root These two polynomials share a common root modulo n, which is m, and we can retrieve it. So we use polynomial GCD to recover x minus m. So why we are doing this is because if m is a root to the polynomial, x minus m will always be a factor. So like David drew on the whiteboard, poly 1 and poly 2 both have x minus m as a root. So we can do poly GCD to get it.
I think of it as we're just applying, I believe in secondary school it's called factor theorem, I'm not too sure. It's
Yeah.
similar idea.
yeah, it is more or less.
Okay, so now I'll just be going through this challenge. So I'd like everyone to follow along. The challenge is called shouting. So
It's in 8D shouting
Yup.
on the CTFD.
So let's look at the challenge. So this is a really short source code. We just have our textbook RSA encryption, but E is 17 this time. Why E is 17? We specifically chose it because Euclidean algorithm takes about like 2-ish hours for 65,537. And of course, we don't have the luxury of time to wait 2 hours here. That being said, there is a faster algorithm, but we will not be covering it today. So we have M1, which is just the flag in integers, and we have M2, which is the flag but louder in integers. So we append louder to our flag. And after that, we just encrypt them. So let's again take our values. So just copy it into a soft script. Okay, but before we embark on our solving process, let's take a look at the difference between M1 and M2. So M1 is bytes too long of flag, and M2 is bytes too long of flag plus louder with a space and a bracket. So let's go back to an example. So let's say our flag is, I'm just gonna work on this soft script, but let's say our flag is I.YCEP test. And so M1 is bytes too long. Y'all don't need to copy this is just a demonstration. I did not print. So if we print M1 and M2, we can see that M2 is substantially larger than M1. But there is an even bigger relation between them. So we recall that when we convert when we convert bytes to integers, we are not only working in big endian because of bytes too long, but each value, or rather each character in the flag or in the message has a different integer. So I like to ask, let's say we make a message 5 characters longer. So let's say we have message is hello and message 2 is hello but with another 5 characters. We don't know these 5. What will happen to the placing of hello? Or rather, should I say the weightage? Remember when we are converting, it will be something like sorry?
Wouldn't the weighting be still the same because of the endian?
No, it won't. Actually, it will be the same for little endian. So we remember that our message is 256 to the power of 4 times ORDH plus 256 to the power of 3 times ORDE and so on, so on, so on. Everyone following so far for why the message is this way? So let's say our message 2 is 5 characters longer. We have message 2 is 256 to the power of 9 because we have 5 more characters times ORD of H and then so on, so on. Everyone following? Everyone understand why this is the case? Okay, great. So now, once we have addressed the placings, we are going to need to account for the last 5 characters, or XXXXX. What we can do is we can do message 2 is equals to message 1 times 256 to the power of 5. Because we're shifting everything in message we're shifting everything in message forwards by 5 characters, which is 256 to the power of 5. Everyone following? I just said a lot of words. If you have any questions, feel free to ask. Message 2 is this, and after that, we are going to need to add our XXXXX. So we can do 256 to the power of 4 times ORDX plus 256 to the power of 3 times ORDX and so on, so on, so on, until we reach our last character. And after that, we notice that message to is just message times 256 to the power of 5 plus bytes too long of message, or rather, no sorry, of x 5 times. Everyone following so far? Everyone understand why we are doing bytes too long, x, 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 x? Okay, great. So we can print M2 again, and we can try to convert M1 to M2 by doing M1 times 256 to the power of, in this case, this whole thing is 1, 2, 3, 4, 5, 6, 7, 8, 9 characters longer. So we can do 256 to the power of 9, and we add the bytes too long of louder, including the space at the start. And if all goes well, it should be the same. And it is. So this is M2, and this is M1 times 256 to the power of 9 plus bytes too long louder. With this in mind, we can go back to our Franklin Rater challenge. And we can see that not only do we have our K, which is long to bytes, or no sorry, bytes too long of louder, but over here our scenario is actually A times M plus K, where our A is 256 to the power of 9. And we have our polynomials now. So we can go ahead and define them. I'm going to comment out everything here. And let's work here. So we can define our polynomial ring, which is Rx is equals to polynomial ring Z mod n. And we can define our polynomials. So the first one will be x to the power of 17. Remember our E is 17. And we need to minus C1 so that it will be 0 when we substitute in our message. And poly 1 is equals to x times 256 to the power of what? Sorry? Yep. X times 256 to the power of 9 plus our bytes too long of louder. Alright, and we need to power it to 17, and we can minus C2. So it will be more aptly named if we were to call our polynomials poly 1 and poly 2 instead of poly 0 and poly 1. But afterwards, we can implement our GCD. So I'm just going to grab the implementation. Oh, never mind. I can't do that. Just have to implement it myself then. Okay, so now we have our poly GCD implementation, and we can get our polynomial with m as a root, so it's x minus m because it's a linear polynomial. And so we can define it as poly 3 equals to poly GCD poly 1 poly 2. And if all goes well, we should get a degree 1 polynomial. And of course I ran it with Python instead of Sage. But oh no, we realized that it says invalid syntax. Why is this the case? Well, this syntax is most definitely invalid in Python, but it is valid in Sage. So we cannot use a .py file, but instead we have to use a .sage file. So I'm going to rename solve.py to solve.sage, and I'm going to go back into the editor. So now if we do sage solve.sage, it should work if all goes well. And of course I did not print it again. So here we have a degree 1 polynomial. And remember, this polynomial is x minus m. So since it is a linear polynomial, this value is just negative m. So we can extract the coefficient directly without having to factor it, and we can convert it to m. So m is equals to int negative, because this is negative m, and then we can extract the coefficient by doing poly 3 0, and hopefully we should get our m, and we do. So afterwards we can do flat is equals to long to bytes m and we can print out flag, but we must remember to import it as well. So long 2 bytes, and hopefully we get our flag. What? That's weird. Okay, I'm not sure why I got the placeholder values when I ran the code with I.YCEP rejected, but whatever, I'm just gonna change it. And hopefully this should give us the flag. Yep, so we have I.YCEP, whispers. Now you know how to apply Franklin Rater. Except that I'm not really whispering. I'll give you guys about 2 minutes to copy this. And afterwards we have a break. So we will be back at about 4:05.
We'll be breaking for